But let me first here now thank all of you for giving these exciting talks and for joining the panel discussion. I can actually see like we have almost everyone here, everyone but Alan. Let me like briefly provide some context here first before we start with the question. So, okay, I'm going to say a few things, and please, I assume no one's really disagreeing with what I will say, but if you do, then interrupt me immediately. Okay, so currently we benchmark mostly on IID test and training test sets, which means like we train car detectors or car classifiers, and then we test them on images that look pretty similar. And that's great, and it brought us to where we are currently, 90-something performance on almost every benchmark. And what we tried here in this workshop is to organize a challenge and a data set where we're actually training on some kind of data, and then we collected specifically with respect to the training data some kind of out of distribution data, right, with respect to certain nuisance variables that are important for computer vision or like in vision applications, right? So variations in shape, pose, texture, blah blah, occlusion. And then we discovered that certain nuisances are more important for different tasks. So we kind of hand collected this data set, which took forever. And but now that it's here and published at ECCV, I hope like people will start looking into this. So we have this concept of out of distribution generalization, and like this workshop is kind of motivated by the statement here, which is that we actually need better benchmarks that measure out of distribution generalization. And I would assume no one disagrees up until here, but if you disagree, then feel free to raise your hand or just speak. I think you guys can just unmute yourself once you want to speak. Okay, so no one's complaining yet. Then let me start with the first question. How should these novel benchmarks actually be designed? Right now, like, shall we really look into, because out of distribution kind of always means with respect to some kind of training data set. So okay, shall we really look into a training data set and then look what the variations we don't see there, and then design like a test set? Or is there like a better way of doing this? And I'm going to also like ask this specifically to Pietro now, because you are one of the pioneers who actually brought us here into this benchmark focused community. Not like just kidding here, but if you like, Pietro, if you have an opinion on this, I would be happy to hear it.
Yeah, no, so you're absolutely right. So far, I completely agree with what you said. So I guess that I would think about both the training and the test set. So if you're allowed to define the training set, so I guess that in competitions, the trouble is that it's difficult to restrict the candidates to one specific training set. At Caltech, we like the webcam, the wildcam challenge, where you train only on, say, 10 wildcam cameras, and you test on new ones. What I've realized is that in computer vision, we are a little bit drugged by the training sets we've had so far, which come from consumer photographs that are being crawled online. And in these training sets, every image is taken by a different person at a different time, against a different background, in different lighting conditions, with a different camera. And so our learning algorithms have the benefit of this huge variety of backgrounds and lighting conditions and viewpoints. So the real challenge I see sometimes in industry and in applications I care about, like ecology, is that the source of training images is one camera or maybe 10, or maybe 100. And what you want to do is to use these very precious few sources to train a system that then you deploy and sell or give, and people will use in millions of different conditions. So if you think of wild cams, you can put a few out in the Serengeti and image your animals. And then you would hope that many environmental conservation organizations can deploy these cameras wherever they are and just use them. So in my mind, we should both focus on training and testing. And now I realize that for somebody who organizes a competition, how do they know or guarantee that the competitors are only training on a restricted training set? That you don't know. And so that's why you're asking a question about the test set. So yeah, I don't know the answer. I mean, it's yeah, we should. So I'll tell you a couple of things that come to mind. So one is, some teams are splicing cutouts of animals or people and so on top of random backgrounds, and so you generate synthetic images that way, and it has to work because even if it's unrealistic, the animal or the person is there, and so you do that. The other one, which I put in place for a team I was leading at Amazon at some point, is to ask the competitors to bring their own training set, and the competition is two-faced. One is, their own test set. The competition is two-faced. One is you write software that has to perform well on the test sets, and the other one, and so you win if your software performs well. The other one is you bring test sets that humans consider to be perfectly fine and that are difficult for the algorithms that your competitors are going to bring to the competition. And so you win by bringing a test set that is challenging. And and so it's a meta response to your question, in which I'm not telling you how to do it, but lots of smart people will come up with very interesting ways of challenging our algorithms, because we know how they work, and they will find the corner cases that put everybody on their knees. And so that's another way to think about it.
I see that it's kind of like sourcing the human. I mean, playing basically this adversarial game with other humans, maybe. I think this also relates to what Olga presented in her like automated capability testing work, right? So do you think like this is, Olga, do you think this is the way of how we should benchmark systems in the future? So train them and then have some kind of automated system that really tries to stress test as much as possible, like whatever, like we do with airplanes nowadays.
Yeah, I mean, I definitely like that idea, right? So sort of like one way, I mean, one way that we've been thinking about actually explainability is that like what you really want for explainability is to sort of show what are the, like, sort of what's the decision boundary of this model. So sort of where is, like, can you kind of outline what is a set of things on which it is going to make correct predictions, and what is sort of the set of things where it starts to fail, and kind of have a almost like a heat map, but in this like multi-dimensional space of capabilities of like what's the probability of kind of failing within this particular setting. I think that's far beyond what current methods are doing. But what I actually thought was really cool from Pietro's comment is the sort of human human in the loop. I mean I think we're underutilizing humans for these testing, and I think this idea of like, have the experts bring test sets that they think are challenging, and like make sure that all of them are run through the same human testing, so that they're not just crazy random images that like humans actually achieve above whatever 95% accuracy on them. And then show those and have a competition around who can break the model the best. Like I think that's really cool. I actually hadn't heard of that idea before, but that sounds great.
I think in some sense we are seeing this when Tesla releases their every once in a while their new self-driving system. People are testing it and then putting the videos on YouTube just to show that they still cannot detect stop signs correctly in certain cases. Because it's a little bit, I mean, this kind of, it's a little bit difficult to kind of design like challenges around this. Okay, I mean, maybe we could actually say, okay, the prize goes to the one who makes the models fail the most, right? Reasonable data. Yeah. Okay, maybe let me continue from here on with a question that actually Alexander showed in his slide deck. Yeah, which I think was very interesting, and therefore I would also maybe like you, Alexander, to give a first take on this. Namely, okay, we have like this concept of distributionship, which kind of indicates something statistical or so to go going on, but it's somehow nowadays everything is a distribution shift, and it's like really difficult to get a hands on or grips on what's happening there. Like, what are your thoughts on if we can conceptualize distribution shift a little bit better, such that we can actually maybe learn something or like talk about it or analyze this concept a little bit more in detail and overcome it?
Yeah, so so there's a reason why I asked these questions, which is kind of, can we make progress here? And just to tie back to the previous conversation, I like what Pietro is advocating. I actually like, my background is also in adversarial robustness, where kind of, like I think the important thing to realize is that there should be no fixed benchmark that says, oh, I am, my method works because there is this benchmark that everyone uses and I'm doing better on these benchmarks. I think the moment we are in that, like mindset, we lost in some sense. So kind of just thinking exactly about like things being adaptive and trying to really like make sure that, distribution shift is actually shifting as opposed to having a fixed benchmark is very important. Having said that, I think we can reuse some of the work, like as Olga was saying, some of the work that people already put into labeling things and gathering data to kind of, recycle some of that work and get new benchmarks out of it. But just like, I'm really very, very, very allergic to statement, this is the benchmark for measuring out distribution shifts. People say, oh, ImageNet-C, it's that. So that's just one point. And this brings me actually to exactly this question, saying like, currently, my feeling is exactly that whenever my model doesn't work, it's because of distribution shift. Adversarial examples are also distribution shift. Like everything is distribution shift, and it's true actually. And in some sense, if only we could solve distribution shift, machine learning would be exactly as we envision it to be. But like I worry that by having this big bag of all the problems kind of being named just distribution shift, we really will fail to make any meaningful progress there. So I think we really should spend time, and especially people who think about these questions a lot, of trying to dissect what are different sub kind of variation of distribution shift, like covariance shift, like even that is too broad, and trying to get us closer to at least making meaningful progress on them. Because to be honest, it feels a bit overwhelming. You just have saying, like you have a method and you can say, okay, we tried this and this and this and it seems to work, but does it really always work? Of course it doesn't. It has to fail, but it's very hard to delineate that. And I think having a more, maybe modest, but kind of crisp understanding of what kind of distribution shifts we might want to focus on first would really do a lot of good to the field.
Yeah, I think that's Oh yeah, this actually relates very closely to what Javier was talking in his saying in his talk about generalization, for example, under different 3D poses, right? So instead of like really saying, okay, this is out of distribution in computer vision, let's say, okay, we have pose variation, and so at training time there will be objects or birds, as in Pietro's talk, in certain poses, and then at test time we will have the similar birds, but in unseen poses. Is this something that you would think is this where we should go, and then kind of find a solution for 3D pose generalization? Or
so let me make a proposal following what Alexander was saying, and let's see if people like it. So there are many ideas that come out of this discussion, which I like a lot. One proposal would be that the models that are offered by the competitors are put there online for experts, which could be other competitors, to examine. And think of what happens for automobiles, for example. You have maybe 5 or 6 leading journals for automobile enthusiasts who do tests on automobiles. And each one of them has their own way of running tests and commenting. And so some test more cornering, some test fuel consumption, some test reliability, and so on. And so all of us have come to the table with different perspectives and different ideas of what these models should be doing, because we have different experiences in our professional life. And so if the models were there and the experts, the panel, maybe were able to test them for a month and come up with different little tricks and test images that they can manufacture in Photoshop, and then write a qualitative report on what they see, what they think the different models are doing, what are the regularities, that would help a lot. And something we do rarely, unfortunately, is go beyond the performance statistics and look through these thousands of images that are being classified by the algorithms and try to come up, by sight with rules or insights as to what's going on, why are they making mistakes, and so on. And often that work is quite revealing, and we can get at the core of a matter with a qualitative analysis, and then we can have a discussion like we're having now, which can generate some hypotheses that can be tested. And so that would be another way to make progress. So are the organizers of this workshop up for organizing the next competition? Is that a discussion we can have now? So give them input and see.
Yes, we are. So we are thinking about it. It is maybe not like the main topic of the panel discussion, but if you have like a pressing or like an interesting idea,
if this discussion can help you organize the next meeting. So I want to bring up another idea that I'm curious to hear how people feel about it. And the idea is this one. So what I've noticed in the last 5 years in competitions is that the winners of the competitions often, the way they win is by ensembling many different solutions or architectures. And if you look at the top few competitors who come close to winning, they all use very similar methods. And the result of ensembling is that the solution is a mush. It's very difficult to understand what works and what doesn't work, because it's all, anything goes. I think, as Alexander was saying, there are many different ways to go wrong, or many challenges in the data that one has to address. And it may be better if competitors address one challenge or the other and focus a lot on one thing or another. The trouble is that if you focus on one thing only, you might be doing that thing really well, but not do well on the other ones. And so you never want to focus on anything because you're afraid of not performing well. So one question for you guys is the following. Let's suppose that the competition platform was doing the ensembling for you. Namely, it puts together all the best solutions that have been proposed, and you get rated on the increment in performance that your own solution gives. And so let's suppose that you're focusing on occlusion, and you may not do very well on cup-sized examples or on lighting changes and so on, but on occlusion you do really well. You let somebody else do the cup sizing and so on, and so you form a team out of the competitors, and you reward the competitors for what they brought to the team in some ways. And now it's a little bit to be seen how to do that, but how does the idea sounds to people?
I think this sounds very interesting, because actually what we found in this competition is that different solutions actually work on different spaces of this nuisance space that we kind of defined. So there are, for example, the first place in the classification track does not perform very well when the texture of the object varies, but it performs well across the other, nuisance axes. But turns out that the second best approach actually performs very well in the texture axis, but not so much on the occlusion axis. So when you combine them, you would actually get like a very, very high performing model. of course, yeah. No, please, Carl.
Oh no, I just want to add one. So I think it's a really good idea is building these types of dynamic benchmarks, so they're always changing. I think it's a fantastic idea. I wanted to mention for the last few years I've been involved in this experiment, kind of trying to look at a similar idea. So the experiment led by Abhinav Srivastava involves CMU, MIT, Ohio State, tons of different schools, where there was a kind of a firewall between two different teams, where one team was trying to build this dynamic benchmark, and the other team was trying to solve the benchmark. And we agreed on ground rules, but after we agreed on the ground rules, we didn't talk. And so the people building the benchmark couldn't reveal anything about what was going to become coming. And we've been working on this for the last 2 or 3 years. I kind of forgot how long we've been working on this, and trying to show. And so I was on the team trying to build the benchmark, trying to build the challenging ones. And one of the lessons that we learned from this is that basically it's a really hard problem, and it was really hard to make any progress. Because one has kind of a reality check that kind of all of our measures of added distribution generalization are basically don't measure the actual performance. These models don't have any ability to generalize added distribution. But what's even worse was, as researchers, there's no way to give feedback as to, or any hint on how we should improve, right? It was too adversarial, right? There's no way for the people working on this to try to make progress, because they just had no idea what was going to be coming next. So I think this is something that's actually important in building these benchmarks. I totally agree we need to move away from the benchmarks, but the good thing about benchmarks in some ways is they do provide some way of giving you a gradient on how you can improve.
So too much dynamic in a benchmark then also makes it really hard.
It becomes too, yeah.
Okay, I see that. I see that Alan is online. Oh, no, he's not. Oh, he was for a brief moment, but yeah.
Maybe I would like to add a small point regarding,
yes.
Well, first of all, Adam, thanks a lot for the invite to this fantastic workshop. So the point I wanted to add is the role of synthetic data sets that get at specific factors in the data. So I understand that data sets that look realistic and so on are interesting for applications, and they are close to what many companies are interested. But if we want to get really a generalization, and we want to get really at understanding how these models work and to trust them, I think synthetic data sets are extremely helpful here, and actually can be extremely challenging, much more challenging sometimes than natural data sets. The big issue of natural data sets is that there may be still underlying shortcuts that the network can use. So it may be that we are not actually evaluating out of distribution generalization, or maybe the models are actually generalizing for reasons that as humans we are not aware. If we generate synthetic data sets that get specific factors like 3D rotation, as I showed in the talk, but you can think about other aspects like a data set of textures, a data set that tries to distill a specific aspect and only has that specific aspect in the data set, that helps understanding better the capabilities of the network to generalize distribution and help us making sure there are no shortcuts, help us gaining an understanding of that specific aspect underlying the visual dimensions. So I just wanted to add this, the role of synthetic data sets. I think it has been underappreciated, most likely because applications and companies that have been funding the field and biasing towards specific aspects.
Very interesting. Thanks for your take on this. Let me, Carol, with like the final. We have so many questions left, but only 4 minutes left on the clock. Let me open the final part of this panel discussions with a question about how can we actually solve. I have an echo here on my. Now it's gone. What is your best guess? Maybe short, such that everyone gets like an answer. Maybe like 1 or 2 minute answer maximum for everyone. What is your best guess on how we are going to solve this generalization problem? And oh, I see Alan is online. So hi, Alan. Thanks for coming. Unfortunately, I can only give you 2 minutes now because everyone will get like for the final round 2 minutes. But what do you think is like your best guess on how we are going to solve the fundamental generalization problem that we have in computer vision? We cannot hear you. You are muted.
Generative models.
Oh, you need to close the the ECCV platform in your browser. We are hearing an echo.
I can't hear you.
Yeah. Can you hear me? Like you have the ECCV platform open in your web browser.
Yes.
You need to close it because it creates an echo.
I think there's little time. Adam, you know what I think.
Okay.
You can say it for me.
Yes. Okay. Let me say, yeah. Okay. We are discussing every week a couple of times. Okay. So what Alan thinks is we need generative models. Generative in the sense that they have a causal understanding of images, that they can actually understand what generates, like what are the causal factors that actually generate this image. It's kind of this analysis by synthesis idea or vision through inverse graphics with a new take on it, which actually says, let's not synthesize images in pixel space, but let's do this in some kind of feature space that is learned and invariant to certain nuisance factors. And certainly these models should be 3D aware and then, causal. So that's my short summary of what Alan thinks, what I think Alan thinks. Let me maybe continue with Javier. What's your opinion on
I think benchmarks like the ones that you guys introduced are definitely essential. I just want to highlight that we need a diversity of benchmarks here, and my emphasis is on the synthetic data sets that help us study fundamental aspects of generalization. So synthetic data sets, I think, are a key element.
Synthetic data sets such that you have full control over training and test data, and can really
exactly.
Okay, yeah, thanks. Then let's continue maybe with Carl. Do you have you want to give it a shot?
Sure. Yeah, I think it's a really interesting question. I guess, I'll be a little contrarian. I'm not sure we'll ever solve it because once we solve one, there'll be another type of distribution generalization we'll want to go after. So I agree. Generative models are really interesting. We've also been working on that, and it does have a lot of advantages for generalization. I think it's a really promising framework. But if I had to make my best guess, I actually think that a lot of this will be solved just by scaling things up. And a lot of these large models are solving a lot of the problems that we are talking about. So sometimes I think we have to reevaluate, like, what types of generalizations do we want? Because if you just scroll the internet, you see a lot of things. I mean, and so I mean that is a promising path.
Thanks. That's I should have probably asked this question in the beginning of this panel because these answers, they are very debatable, and I would, anyway, thanks. This is cool. Yeah, we will organize something like this, and maybe with a little bit more time. Then let's continue maybe with Pietro.
Yeah, I think each one of these suggestions is fine. And again, I would advocate for a diversity of approaches because each one of them can be overfit to some extent. And in my mind, we should also not forget that objects do have structure most of the time. And so if we look for animals, they have a head, legs, eyes, and so on. And I believe that algorithms should demonstrate that they understand the structure of the objects. And if they do, then they are it's not a necessary condition, but it's, I think, sufficient for doing a good job in detecting objects in unexpected environments. So that's another one I would add. So understanding more of the structure of the objects. And the more an object has, so if I saw all of a sudden a penguin walk into my office here at Caltech, I would not not worry for a moment about why is the penguin not on ice. I would just say, oh, why is the penguin in my office? But our algorithms wouldn't see it. Or if a penguin was hanging upside down from a tree, again, he would say, what does that penguin do upside down from a tree? Objects that have no structure are much more difficult to detect in an unexpected situation. So think of a cloud that you typically see in the sky. And now suppose you saw the cloud in the middle of a bush, you wouldn't know what it is, right? You would think that it just looks a little bit hazy down there or something. So I think that structure is something to pay attention to. And if we were able to get parts, attributes, and a skeleton for the object, that would be a good sign.
Okay, thanks. Yeah, I think this is well along also what Alan would have said. Let me continue with Alex and then close with Olga, who actually also started this session. So we'll have this out.
Yes, so I kind of will agree and disagree with everyone before. So I don't think we ever will solve generalization problem, as Carl said. Like there's always next frontier. Yes, like at some point we are kind of getting into like AGI complete problems, and I don't think we are, we are anywhere there close there. I do think that large data and synthetic models will help, but I don't think they will help alone. Essentially just, I think it's very important, I guess, to add a bit of a causal structure, as Alan says, but also to really kind of, to really like provide this neurosymbolic like concepts and kind of add this structure in the priors that Pietro refers to. But just so again, so this is so far like just, agreeing with everyone, but also like, I want to say something. I think that computer vision had a bit too much success to properly deal with this problem. Like, I think we kind of want to jump to the final solution before, again, diagnosing what the problems are and how to get there. And in particular, like, I'm not sure if the dream at this point should be to have this magic model that just like looks at the world and tells us everything we want to tell. I really think we should kind of upfront think of it, it will fail. Like, it will fail, everything fails, this model will fail again. By the way, our vision fails too. What we learn about is just like how it fails and to engineer around this. So I really would like our framework for thinking about computer vision also like say, it will fail. If you claim it will not, think again, it will fail, and start to provide mechanism for understanding and engineering around the failure mode. So kind of, I guess this fits into what Olga was also saying in her talk. Essentially just like, let's think about the whole infrastructure, not just trying to get the model right, but also again, are there any hooks that this model can provide that will signal to us that something goes wrong? If something goes wrong, what will we be able to do to fix whatever went wrong, or at least understand what went wrong? So kind of, I definitely like the generalization problem as a goal. It's a beautiful and inspiring goal, but just like, I think we want to get there in one step, and I don't think this will work, even with all this beautiful, model scale on large data sets, which I'm very impressed with, and so on. So that would be my thought.
Thanks. Thank you, Alexander. And now let's have Olga give the last impression of this panel.
Ooh, that's a lot of pressure.
That's a lot of weight on your shoulders.
I will step up to the challenge. So I will make the claim that I think the solution is going to be in a new student that comes along with a different perspective than any that we've been taking so far. So I don't know if it's going to come from sort of perspectives from cognitive psychology, or perspectives from neuroscience, or perspectives from social science, or perspectives from sort of whatever discipline, but I think that will be the breakthrough. I think so for a couple of reasons. One is that would be my bet for, generally like what is going to be the next big progress in computer vision. I would say it's sort of that. I think the example, if I may, of this is Feifei and ImageNet. Like, one way of thinking about ImageNet. So all of us said this yesterday. I thought this was a very like beautiful way of putting this. Is that one way of thinking about ImageNet is a massive psychophysics experiment, right? So you show a ton of people, a ton of photos, and you ask, is this object in this photo and then you sort of accumulate all of this data, and the inspiration behind that data set really came from like psychophysics and came from Fei bringing background from neuroscience and from sort of studying human vision, and that led to like a fundamental sort of rethinking of how we do visual recognition, how we think about scale, the importance of data. Like a lot of that sort of came from that insight. And so if I were to bet on what the next one is going to be, I think it's going to be something that kind of has that flavor. So all the students out there, we're counting on you. Come on in. Like hopefully you had a diverse training and diverse backgrounds and in sort of different fields. So tell us, like, what's the next cool thing?
Thanks. These are fantastic last words for this workshop. We didn't synchronize this, we didn't plan this, but these are like, perfect. So with this, I'm going to thank all of the invited speakers. Thanks again also for taking the time to join this panel discussion. I just realized I should have designed this in a different way, and maybe also set it for an hour, because there are so many things to be discussed here. And also a big thank you to all of the participants. We are looking forward to seeing you next year, hopefully. Thank you, everyone, and have a good time.
Thank you for organizing.
Thank you for organizing.
This was very interesting.
Thank you.
Thanks.
See you guys.
Thanks.
Bye.
See you.
Thank you, Adam.
Thank you.